In this lesson, we're going to cover asymmetric algorithms. Now, unlike symmetric algorithms, asymmetric algorithms do not require a shared secret key. For this reason, we often refer to them as public key cryptography because their key is considered to be freely and openly available to anyone in the public. Now, with asymmetric algorithms, we're going to use a key pair to encrypt and decrypt our data using two different keys. These are known as a public and a private key. Now, public key cryptography can provide us with confidentiality, integrity, authentication, and non-repudiation for the different pieces of data or messages being sent. To provide confidentiality of the data needs to be encrypted using the receiver's public key. So, if I want to send a document to my friend Mary, as you can see here on the screen, I'm going to encrypt that document using Mary's public key. By doing so, only Mary is going to be able to read it because only Mary is going to have Mary's private key. Now, this is going to be used to decrypt the contents and ensure the message I sent is safe from anybody else's prying eyes. Now, once I encrypt this data that I'm going to send to Mary using her public key, nobody else in the world can read it except for Mary. Even I can't read it, and I was the sender because I can't decrypt the information because I only had her public key, not her private key. So essentially, when I encrypt it, it's a one-way encryption when I use a public key because the only person who can decrypt it and get it back to readable plaintext is going to be the receiver using their private key. Now, when it comes to non-repudiation, this message should be encrypted using the sender's private key. So in this case, I can encrypt that message using my private key. When I do that, anyone in the world can decrypt that because my public key is out there in the open and anybody can download it and then open that message and read it. That isn't going to give us any kind of confidentiality if I encrypt a message using my private key. Instead, what I'm worried about here is making sure that people know I really was the person who sent that message. And that is non-repudiation. Now, to make sure this happens, only I can sign it using my private key because only I have that private key. Now, in most organizations, we don't want just confidentiality or non-repudiation. We want both of those things. And in addition to confidentiality and non-repudiation, it'd be great if we could have integrity and authentication as well to make sure the message being sent is going to be sent where nobody can read it, we know where it came from, and that it wasn't changed in transit. Now, to accomplish all of this with our emails, we often use a process to create a hash digest based on the message being sent, and then we encrypt that hash digest using the sender's private key. This is known as a digital signature, and it's going to provide us with the integrity of the message that's being sent because we have that hash of the message, as well as giving us non-repudiation because only the sender could encrypt that hash using their private key. Then, we take the message that we're going to send and we encrypt it using the receiver's public key. This will give us confidentiality of the message because only the receiver can decrypt the message itself. So now I've got integrity of the message using the hash, I have non-repudiation by encrypting that hash using my private key, and then we get confidentiality by encrypting the message itself using your public key as the receiver. So now that you understand how asymmetric algorithms work at a basic level, let's look at some specific asymmetric algorithms that you may encounter while working as a cybersecurity professional, including Diffie-Hellman, RSA, and ECC, also known as elliptic curve cryptography. First, we have Diffie-Hellman. Now, Diffie-Hellman is named for its two inventors, and it's used to conduct key exchanges and secure key distribution. In fact, Diffie-Hellman is widely used whenever you're setting up a VPN tunnel or other encryption tunnels that require a symmetric algorithm's shared secret key, which is a private key, to be exchanged first before setting up that symmetric tunnel, and then using asymmetric algorithms like Diffie-Hellman, we can do that in a secure and scalable manner. Now, Diffie-Hellman is also susceptible to on-path or person-in-the-middle attacks. So if you want to secure yourself, you need to make sure you have some form of authentication, such as requiring a password or a digital certificate at the beginning of that exchange process. Now, whenever you see Diffie-Hellman, I want you to remember two main things. First, this is considered to be an asymmetric algorithm, and second, it's going to be used for key exchange inside of creating VPN tunnel establishment as part of IPsec, or to be able to do a key exchange of any kind over the internet. Second, we have RSA. RSA was named for its creators, Ron Rivest, Adi Shamir, and Leonard Alderman. RSA is widely used for key exchange, encryption, and digital signatures, and the algorithm itself relies on the difficulty of mathematically factoring large prime numbers, and this helps protect its public and private key pairs. RSA can support key sizes between 1024 bits and 4096 bits. Now, RSA is widely used in organizations around the world. If you happen to have one of those secure tokens on your keychain, where every 30 to 60 seconds that 6-digit number changes, and you're going to use that as part of your login and multi-factor authentication, well, guess what? You're actually using RSA because that token is storing RSA asymmetric one-time use keys that you're going to enter in as a form of authentication, showing you have possession of that token. Third, and finally, we have ECC, also known as elliptic curve cryptography. Now, elliptic curve cryptography is heavily used in mobile devices, and it's based on the algebraic structure of elliptical curves over finite fields to define its keys because it's very efficient and a great way of providing better security than an equivalent RSA key of the same size. In fact, ECC's algorithm is about 6 times more efficient than an RSA algorithm. So, if you're going to have a 256-bit key with ECC, you'd actually have to have a 2048-bit key with RSA to be just as secure. For this reason, you're going to see ECC used in a lot of things like tablets and smartphones and other mobile-based implementations because these devices have much less processing power available than a standard desktop or laptop might. Now, there are a few variations of ECC as well that you may come across in the field, including ECDH, ECDHE, and ECDSA, so let's talk about those. ECDH, or the elliptic curve Diffie-Hellman, is an ECC version of the popular Diffie-Hellman key exchange protocol. ECDHE, or the elliptic curve Diffie-Hellman ephemeral protocol, is another variant, and this one uses a different key for each portion of the key establishment process inside of the Diffie-Hellman key exchange. ECDSA, or the elliptic curve digital signature algorithm, is going to be used as a public key encryption algorithm by the US government for all of their digital signature needs. Now, whenever you hear the term elliptic curve cryptography, or ECC, I want you to remember that ECC and all of its variants are most commonly used for mobile devices and low-power computing devices because they give you an equivalent level of protection to other asymmetric algorithms with a lower key size, which means they require less processing power to encrypt and decrypt the data. So remember, when it comes to asymmetric encryption, also known as public key cryptography, there is this system of encryption in place that's going to use 2 different keys, one for the encryption and one for decryption. There are 3 basic types of asymmetric algorithms you should be aware of, which are Diffie-Hellman, RSA, and elliptic curve cryptography. Diffie-Hellman is focused on conducting key exchanges when you're creating VPN tunnel establishment as part of the IPsec protocol. RSA, on the other hand, is widely used for key exchange, encryption, and digital signatures. Elliptic curve cryptography is an asymmetric algorithm that's heavily used for encryption by mobile devices, tablets, and other low-power computing devices.